Hello, this is Group 5B. Today we'll be talking about the Plato Resistivity Lab. First, I wanted to review some of the basic vocabulary we had learned this semester. Current refers to the flow of moving charge throughout a circuit, while resistance is the opposition to this flow of charge, described as the inverse. The voltage is the difference in potential energy per unit charge. Battery creates a voltage difference between 2 points of the cell. It pushes the electrons in the circuit, creating the current. Ohm's law describes a relationship where voltage equals current times resistance. While resistance specifically refers to the opposition of charge flow, resistivity is based on the resistor's composition and its dimensions, and how that relates to the resistance of a resistor. Rho, or resistivity, equals the resistance multiplied by the cross-sectional area and divided by the length of a resistor. Longer and larger resistors will offer less resistance, and resistivity values are specific to each material. Circuits can be built in series, in parallel, or both. A series circuit has only one path for the current to travel, as can be seen in the top left image. The current remains constant throughout, but the voltage will drop after each resistor. The loop rule says that the sum of all the voltage drops in a loop equals 0, and the total resistance equals the sum of each resistor. While parallel, branches in the circuit form junctions. There are multiple paths that the current can take, so the voltage will remain the same throughout the loop, but the currents will split at each of the junction sites. The net current flowing to the junction must equal that same current coming out of the junction. The reciprocal of the total resistance will equal the reciprocal of each of the resistors summed. The goal of our experiment was to build a circuit containing an LED bulb and electric motor in parallel. Additionally, we wanted to calculate the resistivity value of the Plato resistor we created. We used current-limited motors and voltage-limited LEDs. That current must flow through at least 20 milliamps for it to light up. We had 3 1.5-volt batteries and used a multimeter to measure voltage and current. On the left, we can see our fully functioning circuit with the fan and the LED bulb. On the right, we see a paper diagram of this. There are 3 1.5-volt batteries, pushing the current towards the light bulb. Some of the current splits at the first junction and goes into the current-limited motor, allowing it to run, while the rest of the current flows through the resistor, causing a voltage drop that fits within the voltage-limited capacity of the light bulb.
For our pre-lab, we used a Plato resistor shaped as a cylinder in a circuit with no other components. We measured the cross-section area and the length between the wires, and we measured voltage drop and current, used those values to calculate resistance, then used that resistance value to calculate resistivity, running in parallel with the Plato resistor and an LED bulb. While measuring current across the Plato resistor, we noticed that it was extraordinarily low in the microamp range. This affected our resistance and resistivity calculation, causing a abnormally high resistance value and thus also an abnormally high resistivity value. In regards to the precision of our experiment is relatively consistent, as if you account for measurement error, voltage drops are approximately equal across both loops. Current through the loop with the higher resistance is significantly lower than the one of less resistance, and the sum of the currents through both loops is equal to the current through the battery, or the total current. We figured out that our vastly different values in calculated resistivity had nothing to do with the Plato resistor, but the LED bulb in series with the resistor. The LED's semiconductor properties caused the resistance to change over time in a nonlinear fashion, but as an upward curve of sorts that significantly increased the resistance along that loop.
Sources of error include the precision of the voltmeter, the non-ohmic properties of Plato and the LED, the dryness of the Plato, the inconsistency of the distance of the solder gap inside the Plato, because we had to continually replace the solder, and the properties of the motor. The non-ohmic factor can be mitigated by using a variable voltage source to carefully determine the resistance curves of each component. As for the solder, we can use something that oxidizes much slower so we don't have to replace it and the gap between the electrodes stays consistent. To mitigate dryness, we can use something that doesn't dry out, like plasticine.